Okay, good morning or good afternoon, depending where you are, and thanks to the organizer for this opportunity. I will discuss today about our study on the disk evolution in Dolidze25. Now, in this conference, I don't think I need to introduce star formation and the protoplanetary disks and why we are interested in the dispersion of these structures. I want to jump directly on the topic of this seminar and start discussing about the feedback provided by the environment on the dispersion timescale of disks. We know that the environment can affect the dispersion of disks mainly by two mechanisms, which are the photoevaporation induced by the UV radiation emitted by nearby massive stars, as it is occurring in the disks in nearby Theta 1 Orionis in the trapezium, and also by close encounters, by the gravitational interaction between the stars of the same cluster during close encounters. For instance, you can see here on the left, these are simulations of the final morphology of a disk affected by a close encounter between two stars. And as you can see, by changing the parameters of the interaction, you can result in a completely different morphology of the disk itself. And there is a lot of papers demonstrating the effectiveness of the environment feedback on disk evolution. This list is absolutely not complete at all. But let me also say that this feedback is important even from a cosmological point of view. And the reason for this is that what we know is that this feedback is effective when the UV radiation, local UV radiation in a stellar cluster is very high, so this cluster is hosting a very large population of massive stars, and when the stellar densities are pretty high. And in the Milky Way today, these requirements are met only in the core of the very massive clusters or in the very few superclusters in our galaxy. We know only 6 starburst clusters in our galaxy. But we also know that the superclusters were quite common in the early universe, in young galaxies with intense star formation activities, in starburst galaxies, or in galaxies during emerging process. This means that the effectiveness of this feedback from the environment changes during the evolution of a galaxy. For instance, let's consider M51, which is an interacting galaxy. Some people have identified the superclusters in this galaxy, and the mass distribution of these clusters is shown on the right, compared with the mass of the 5 in this case super cluster in the Milky Way. And as you can see, M51 is hosting a larger number of superclusters, and most of them are even more massive than the one in the Milky Way. We also know that there is another important properties of the environment which changes with the time, and this is metallicity. So it is quite important also to understand whether the dispersion timescale of a protoplanetary disk can be affected by metallicity. And you can expect this effect because if you consider an unperturbed disk, we know that the dispersion of this disk is mainly driven by the accretion and by the photoevaporation induced by the central star. And both phenomena actually can be affected by metallicity. For instance, accretion is driven by the magnetorotational instabilities, which depend on the ionization of the disk. Ionization of the disk can be higher in low metallicity because cosmic rays can penetrate deeper in the disk, and the UV radiation, the energetic radiation, can be less absorbed. And for photoevaporation, these arguments hold because UV radiation can penetrate deeper, is less absorbed because of the smaller amount of dust, and then you can have higher photoevaporating rates. And this has been actually demonstrated by some theoretical work. For instance, on the right I show you the results of some simulations in which the photoevaporation rate of a disk at different metallicities is measured on average of a few thousand years at different locations in the disk. And as you can see, after a threshold at a very low metallicity in which there is an effect, then the photoevaporation rate increases and start decreasing with increasing metallicity. So there is an effect which can be quite important. Now, from the observational point of view, it is quite difficult to measure this effect because low metallicity clusters are typically or in the outer galaxy or in other galaxies, so pretty distant and very difficult to reach. There are two exceptions to this. One are is the investigation by Yasuda and collaborators who analyzed six star-forming regions in the other galaxies. You see here the name and the properties of these clusters, which have a very low metallicity. They found the members of these star-forming regions by means of infrared photometry, found the stars with disk, calculated the disk fraction. The results are shown on the right. You see that the disk fraction in these clusters, which are the red dots, are quite low, lower than the disk fraction of solar metallicity clusters, which are the black dots, meaning that in this low metallicity environment, likely the protoplanetary disk disperse quicker than in solar metallicity. Quite different results have been obtained in the Large Magellanic Clouds, in which some authors have identified the accretors by means of photometry using also narrow H-alpha filters. And they also have estimated the properties of these accreting stars by analyzing their photometry. And what they found is that not only the accretion rate are typically higher in these low metallicity environments compared with the solar metallicity clusters, but the accretion also lasts longer because these stars are on average older than the one in the Milky Way. So more intense accretion and an accretion that lasts for a longer time, which can be a consequence of all the effects we discussed before, like more effective MRI, for instance, or even a slower formation of solid bodies, which allow the disk to live longer. It is quite difficult to understand what is the effect of metallicity. In order to try to understand this, we are analyzing the star formation activity in Dolidze25, which is a very young cluster known to be with low metallicity. Actually, it's quite close to the Sun, between 3 and 5 kiloparsec. These are wonderful Spitzer images of this region in which the cluster is present in the cavity, in the center of this cavity. We marked with these dots the members that we have identified with disk in blue and without disk in green. Another important properties of Dolidze25 is the fact that it doesn't have an important OB population, and it is with low stellar density, which means that you don't expect effects from photoevaporation or from close encounters. So we can study the effects we can isolate the effects of metallicity. The main data set that we analyzed is provided by ASIS Chandra SSI, and in these images you see the field of view of ASIS. We have analyzed the two copoint and Chandra observations. I show you on the right, for a total exposure of 145 kiloseconds, which allowed us to identify 618 X-ray sources. And we merged this X-ray data with existing optical and infrared data of this region, with the aim of selecting the members of the Dolidze25, both with and without disk. For the stars with disk, we used an algorithm which is based on about 20 optical and infrared color and color magnitude diagrams, together with a procedure which is aimed to select and discard all possible contaminants. You see here the scheme of this procedure, in which you enter every single star and you test whether this star can be a candidate giant in the background, an extragalactic source, or other kind of possible contaminants. And the final list of stars with disk counts 647 stars, 220 inside the ASIS field of view. And in this field of view, we also identified the 432 stars without disk, mainly from the X-ray sources with optical and infrared counterparts. We estimated that our sample of members is quite complete, between 0.7 and 1.5 solar masses. You can see here on the left the mass distribution of our members, the comparison of the slope in this mass range of the mass distribution compared with the Salpeter-Krupp IMF slope, and you see that they are quite similar, meaning that in this mass range our sample is quite complete. And this allowed us to also calculate the disk fraction in this mass range in Dolidze25, which is found to be about 37%, with a median age of the cluster of 1.3 million of years. Now, on the right, we compare the disk fraction of Dolidze25 marked with a star with the disk fraction of several other clusters in the Milky Way. And as you can see, if you compare the clusters at a similar age, that the Dolidze25 is characterized by a low disk fraction, which is actually comparable with the disk fraction of the massive clusters in which photo operation and close encounters are important, which are marked with these red dots. This is a suggestion that in the Dolidze25, which I repeat is a cluster with low metallicity, disks are dispersed quicker than solar metallicity cluster. We say that this evidence is quite marginal because it relies on the estimate of the stellar ages from photometry, and we know that this can come with several intrinsic uncertainties that it's very difficult to account for. So I leave you here with the conclusions. We analyzed this large data set of based on Chandra and optical and infrared catalogs of Dolidze25. We have identified the members of this very interesting cluster, estimating also the stellar parameters from optical photometry, and we calculated the disk fraction of Dolidze25, finding that it is quite low compared with the other clusters with similar age. And this is actually similar to the disk fraction found in clusters with significant population of massive stars or dense cores, in which photo operation or close encounters can be important. So this is an indication that in a low metallicity environment like Dolidze25, the dispersion timescale of protoplanetary disks can be lower than what we observe in solar metallicity cluster. And this is all. If you have questions, just send me an email and we can discuss about it.